So let us start today's session. So hello and welcome to this NPTL TA session for the heat transfer course. And this is week 10. So we will be discussing some questions related to week 10's course content. Okay. So let us start with the first question today. So first question is uh, water. Okay. Water is boiled at atmospheric pressure. Water is boiled at P equal to 1 atmosphere by a horizontal polished copper heating element. Okay. So it will be better if I draw the setup. Okay. So let's say we have something like this system. And in this, we have, let's say, one heating element which is attached something like this. Let me draw one more. So you see, here we have a heating element that is attached. Okay, something like this. Mm, So better if I do it like this only. So this is a heating element. Okay, and it is a, let's say it will be attached to this. So it is attached. Okay, to this something like this. And say we have vapor liquid up to this particular region, something like this, and this is at 100 degree Celsius. Okay. And here we have vapor film that is being generated. So let me draw it in different color so it will be useful. So there is a vapor film. Okay. Okay. So this is, and here we have the, this is the heating element. Okay. So this and this. So this is the heating element, and this is the vapor film. And from here we have vapor that is going out. Okay, because we are heating it, right? So it will be evaporating, and here pressure is nothing but 1 atmosphere. Yeah, whatever liquid you have. Okay, so let me tell the question what it is. So water is boiled at atmospheric pressure by horizontally polished copper heating element. Okay, so this is horizontal. Let me write polished copper heating element. Okay, and this element has a diameter of 5 mm and emissivity of 0.05, and this is immersed in water, right? So this is water. Okay, this is water. Okay, the surface temperature of the heating wire is 350 degrees Celsius. So let me write Ts, which is the surface temperature of the heating wire. Surface temperature of heating wire. This is equal to how much? 350 degrees Celsius. Assume steady state operating conditions exist. Assume steady state. Okay. And there are some things that are given, that is the properties of water at saturation temperature. So properties of water at saturation temperature. Okay. So in this saturation temperature, all the properties are given at, let me write T sat- saturation. Okay, HFG is equal to 2257 times of 10 to the power 3 joules per kg, and density is equal to 957.9 kg per meter cube. And properties of vapor at the film temperature. Okay, so this is property of water, and similarly we have property of vapor at film temperature, that is TF, which as you know is nothing but Tsat plus Ts divided by 2. So this is the average temperature, which if you do is nothing but Tsat is how much? Okay, Tsat is not given, right? Okay, so this is 225 degree Celsius. Okay, at this temperature, the properties that are given is density of vapor is equal to 0.441 kg per meter cube. Viscosity of the vapor is given to be 1.73 times of 10 to the power of minus 5. Cp of the vapor is nothing but 1977 joule per kg degree Celsius, and K of vapor 0.0357 watt per meter degree Celsius. And to calculate the correlation, like you can use a correlation to calculate the film heat flux. So you can use this correlation. Q dot of film is equal to C film times of G KVQ rho V rho L minus rho V HFG plus 0.4 CPV times of TS minus TE sat. I think I better do it like this. And this whole thing divided by mu V times of D times of TS minus T sat. Okay, and this to the power of 1 by 4. And then again you have Ts minus Exactly. You can use this expression. And the C film you can obtain. This is C film. So there are two ways through which you can obtain this. So this is 0.62 for horizontal cylinders and 0.67 for spheres. Okay. So there are two bits to this question. So first bit, I'll write the question and then you try solving it. Then we'll discuss the solution and then we'll move on to the next bit. So the question is determine the heat flux. Determine the heat flux. Okay. Heat flux from radiation, that is Q dot dot RAD, radiation, from the wire to the liquid. So you can calculate the radiation per unit length of the wire. So that is nothing but a radiation per unit length of the wire. Okay. So you can calculate using the Stephen Boltzmann law that you know that Q dot of radiation is nothing but epsilon sigma Ts to the power of 4 minus Tsat to the power of 4. Okay. And you know what is this sigma is nothing but 5.67 times of 10 to the power minus 8 watt per meter square Kelvin to the power of 4. So first you have to calculate this. So you can see the entire question. So you can try and then we can discuss the solution. So Tsat you can take 100, correct? So from there you can easily calculate. Okay, so let's see. So determining flux is very much straightforward. You know, so you can use this particular form of Stephen Boltzmann's expression by substituting all the values. So let's see. So Q dot of irradiation is equal to epsilon sigma Ts to the power of 4 minus T sat to the power of 4. Uh, this epsilon value is already given, 0.05. So this is 0.05, and this is 5.67 times of 10 to the power of minus 8. And Ts, as you know, is the surface temperature, that is 350 degrees Celsius, but we have to convert it into Kelvin. So plus we have 273, and similarly Tsat is nothing but we have 100 degrees Celsius plus we have 273. Correct? So if you substitute everything, if you substitute all the things, you will be getting Q dot of radiation is equal to 372.2 watt per meter square. Okay, so this is quite straightforward, right? Now let's go to the next bit. So the second is determine the total heat flux. Okay, determine total heat flux. So we can write something like Q total, Q dot of total. Okay, per unit length again. Okay, so this is total heat flux per unit length using the following correlation. Okay, it is given that Q dot of total is equal to Q dot of film plus we have Q dot of this radiation. Uh, okay, so Q dot of radiation. But there is another factor they have given, that is it's multiplied by say 3 by 4. Okay, so using this correlation, you calculate the total heat flux per unit length. So again, you can give this a try and then we can again discuss how to solve this. I think solving it is pretty much straightforward, but we can see what is the final value. Okay, we can check for the final value. So let me zoom out. So if you remember this, I am focusing it here so that you can see all the data. Okay, so let's see. So we already have Q radiation, so that we can directly substitute from here. So this we already have Q radiation, right? So we can directly substitute Q radiation from here. But this Q film that we have, that this we don't know. So we have to obtain this Q film. And to get this Q film, we can use this particular expression for Q film, right? So uh, let me write it here. So this is the Q expression. Now you see, uh, here we have this excess temperature that we have Ts minus Tsat. So this we already know. What is this? This is nothing but 350, that is surface temperature, and this is the saturated temperature for water. So the difference will be nothing but obviously 250. And therefore, you know, the film boiling will occur. Okay. And which value of C we can take? So obviously this is the case of a cylinder. So we can use, yes, we can remove this and we can use 0.6. Yes, this particular form for cylinder. Okay. All the values you see are given. So this difference we already know. This is the same difference. This G, this KV, rho V, these are all given. Here you can see this rho V is given. This mu V is also given. KV is also given. CPV is also given. Rho L minus rho V, CPB, mu D, everything is given. You can substitute all the things and then you can get Q dot of film is equal to how much? 5.93 times of 10 to the power of 4 watt per meter square. Okay. And therefore, the total, we can just find out the total heat flux, that is Q dot of total is equal to Q dot of film plus 3 by 4 times of Q dot of radiation. Okay. So this is nothing but Um, 372. This is Q dot of film, so 5.93 times of 10 to the power of 4, plus we have 3 by 4 times of 372.2. Point. Okay, so you can see this is very very small, and so you can still add in total to get uh, this to be equal to 5.96 times of 10 to the power of 4 watt per meter square. So this is the Q total. Okay, now let's try to see another question. So this question will be mostly, you know, based on understanding only. Okay, so let me draw and then we can see. So there are kind of four regions. Okay. Okay. And we have okay. How much it can happen? It can happen. Okay. So this is the excess temperature, that is delta T excess. Okay. So this is nothing but Ts minus Tsat in degree Celsius. And look it here. Hmm. So this is a around 5, and This value is say around 10. This is around say 30, and we have somewhere here 100, and this is say close to say 120, something like this. Okay, so you can see there are uh, four regions. We can name these as, let's say this be A, and this region be B, this point be, let's say, C, and we have something here that is, let's say, D. Okay, and in this we have this as Q dot of boiling. This is unit of watt per meter square. And if you go by scale here also, you can similarly have scales here, kind of something. This is, let's say, 10 to the power 3. This is, and it goes up to say 10 to the power of 6. Okay, so this be 4, this be something 10 to the power 4, 10 to the power 5, 10 to the 6, something like this. Okay, yes, I missed one point here. This is, let's say, point E. Okay, so you can see this graph. So this, what is this? This is a typical boiling curve for water, right? So boiling curve for water at say pressure equal to 1 atmosphere. Okay, so okay, let this not be a question. So I'll let you know some idea. So it will be kind of a discussion. Let us keep it. Okay. So you see this region CD. So all the points you know. So what are different regions that you have already studied in the course content? So if you remember this region CD, it falls in the transition boiling regime. Correct? And also in the nucleate boiling region, this agitations that are caused by the entrainment of the liquid to the heater surface, they are primarily responsible for the increase in heat transfer coefficient and the heat flux during the nucleate boiling. Correct? And also one more thing you can remember in this curve is that this nucleate boiling is kind of the most desirable regime in practice. Okay, this uh, uh, because of this high heat transfer rates. Okay, very high heat transfer rates can be achieved within this particular regime. Okay, okay. Let me ask you one question. Let's say in the region CD, what do you think that is it? that a large fraction of heat surface is covered by vapor film. Is it true? And because of this vapor film, it acts kind of a like a insulator because of the low thermal conductivity of the vapor relative to that of liquid. Is it true? Exactly, this is true, right? In this CD region, why is this heat transfer decreasing? Because if you see, once these vapors are generated, uh, something like this, let's say we have a liquid, and if you see, vapors will be generating something like this. So you see, they will kind of block the heat transfer rate from the surface. So initially, if it was high heat transfer coefficient, now because of this particular medium that we have, this heat transfer coefficient of air is actually low, and therefore the heat transfer rate will also decrease. And that is why you see there is a decrease in this particular regime. Okay. Okay. And I can ask you more questions on this also, like which is better, like a drop wise condensation or a film wise condensation, which is better? So this is a very typical question that you can expect. So for drop wise condensation, only a fraction of the surface is exposed directly to the environment. Whereas for film wise condensation, a blanket of liquid film adds extra resistance to the transfer of the heat. Therefore, it lowers the heat transfer from the surface. Okay. Okay. Let's do another question. I think we have discussed enough. Also, another thing, like uh, you see this particular shape of this particular boiling curve, the shape. You see, it goes here and then increase and then decrease. So this particular shape of the boiling curve, does it depend on the geometry? You think about it. Yeah, like that the range could be different, but I'm talking about the shape. Will the shape of the boiling curve will depend? Will it depend on the geometry? So basically, it will not be dependent on the geometry. It will be independent of the geometry. Okay. Okay. Now let's move on to the next question. So we'll in this question we'll consider a kind of a power plant. Okay. So steam in the condenser of a power plant. So we have steam in condenser. So this is the system. The power plant is to be condensed at a temperature of 30 degrees Celsius with cooling water. Okay, and this cooling water is, let's say, from a nearby lake. And this enters the tube of the condenser at 14 degrees Celsius and therefore leaves at 22 degree Celsius. Surface area of the tube is equal to 45 meters square, and the overall heat transfer coefficient H overall is equal to 2100 watt per meter square degree Celsius. So you can see in this type of situation, the heat transfer coefficient values will be very high. And this condenser is well insulated. Okay, so condenser is well insulated. Now, what does this mean? The heat loss to the surrounding is negligible. So we can do one thing. Let me draw the system so it will be better. Okay. So let's say this steam is coming in. Okay, and so this is steam, and let's say this is 30 degree Celsius, and here also it is living at 30 degree Celsius. And this is used to say heat of for heating of okay, we'll do this, but obviously if it is coming, then we can say that, let's say we have some of the steams will be here, right? It will not be vacant, something like this. And then we can draw a system. We can use this also. So this looks bad. So here we have this is cooling water that is going in, and this is going in at, let's say, 14 degrees Celsius, and it is coming out at, say, 22 degrees Celsius. So I think now you can particularly visualize the system. Okay. So we given various datas are given. So let me write. So the heat of vaporization of water, okay, at 30 degrees Celsius. So heat of vaporization of water at 30 degree Celsius. So this that is HFG is equal to 20431 kilojoule per kg, and the specific heat of cold water. Okay, so specific heat of cold water at an average temperature of 18 degree Celsius. We write specific heat of cold water at average temperature of, say, 18 degree Celsius. So this CP is actually given to be 4148 joule per kg degree Celsius. So let's try to solve this bit by bit. Okay. So the first question is, determine the heat transfer rate. Heat transfer rate in kilowatt in the condenser. So we can see how to do this. Okay, let's see. So we have two ends of the cooling water. One is at 14 degrees Celsius and one is at 22 degree Celsius. So the temperature difference between the steam and the cooling water at both the ends we can write. Say let's say delta T1 is equal to 30 minus 14. So this is equal to okay. Let's say let me write this 22. Okay. So this is 8 degrees Celsius. And similarly, let's say delta T2 is equal to 30 minus 14. So this is equal to 16 degree Celsius. So now we can calculate the log mean temperature difference. Okay. Now log mean temperature difference. So this is equal to, we can write delta T LMTD, log mean temperature difference. This is equal to, as we know, is delta T2 divided by delta T1. Sorry, delta T2 minus delta T1 divided by ln of delta T2 by delta T1. Right? So this is equal to how much? 16 minus 8 divided by log of 16 divided by 8, that is 2. Right? So this is, if you calculate, you will be getting 11.5 degree Celsius. So since you have calculated log mean temperature difference, now you can calculate the heat transfer rate. So heat transfer rate Q, let's say dot, is equal to nothing but overall heat transfer coefficient A delta T LM TT. So instead of H overall, we can write here U. It will be better, right? U. So this is equal to 2100. We have A, that is the area which is already given to us, that is 45 meters square. And then we have delta T LMTD, that is 11.5 degree Celsius. So this is equal to 1.087 times of 10 to the power of 6 watt. Okay, or in better way also you can write, let's say 1087 kilowatt. Any way you can write. Okay. Now let's see the second bit of the question. That is Determine the mass flow rate of the cooling water. So that's in kg per seconds of the cooling water. So you can try this and then again also we can discuss. It's a little bit tricky, but it's easy. It's not very complicated, but just think how to do it. Okay, so let's see. So this is again very straightforward, but you have to think a bit. So we have m dot of cooling water. Okay, so how do we find that? So what you can do is, so the q dot that we have, which is nothing but m dot cp times of t out minus t in, is nothing but the same for the steam, that is m dot of hfg, and this is for the steam. For the phase change, how much steam, like the steam is changing its phase, right? So for that case, the heat, you see the heat it will gain, that heat will be used for the phase change of the steam. Okay, so we can see this m dot of cooling water we can calculate from q dot, that is 1078 sorry 1087 1087 divided by 4148 times of the cp times of t out minus t in, that is 22 minus 14. So this is equal to 32.5 kg per seconds. So next question I would have asked you, what is the m dot for the steam? Okay, so what is the flow rate of mass flow rate of the steam? So similarly you can calculate from that side, nothing but 1087 divided by this hfg, which is 2431. So if you do that, you will be getting 0.45 kg per second. Now I'll tell you one interesting. I'll not give you as a question, but I'll show you. Okay, that will be better, so that you can get a feel of how to do this. So we'll take a practical example. Okay, so it will be better for you to understand. Okay, practical situation will take. Say, consider a saturated vapor from a chemical process condenser. Okay, and it is condensing at a slow rate on the inner surface of a vertical thin walled cylindrical container. Okay, so let me draw this so it will be much more useful. So consider a cylindrical container. So I'm doing the side view. So let's see. This is a cylindrical container, and some saturated vapor from a chemical process is condensing at a slow rate on the inner surface of a vertical thin walled cylindrical container. Okay, and this is say of length L. Let me draw here. Say this is Let me write with a different color so it will be not be confusing. L. And vapor is condensing, so let me draw with orange. Something like this on the inner walls. And this has a diameter of, uh, let me close this. And this has a diameter of, let's say, D. Okay. The container wall is maintained at a uniform temperature Ts. Okay. So this is maintained at a uniform temperature of, let's say, T, by flowing cold water across its outer surface. That means how? So we are taking some cold water, something like this, and let's say it's coming from here. Okay. So cold water. This is what helps in maintaining a temperature of T. Okay. Let me close this. It's not looking good. This is the condenser film that we have. So this is nothing but a condenser, condensing film, we can say condensate film. So and this film is coming from set-top, as I mentioned. It's coming from here, saturated vapor. And set temperature T sat, we can say. So we have to derive an expression for the time required to fill the container with condensate. Okay. So you can see it will come down and it will condense and it will fill this container. It's a cylindrical container. I have not written, right? Okay, so this is a cylindrical container. So we will derive an expression in how much time required to fill the container with condensate, assuming that the condensate film is laminar. Okay, and we will express it with known values of this these parameters that we know. So this is nothing but this Ts, right? This is Ts. So you understood the question. This is a cylindrical container. Saturated vapor is coming in and it is condensing because of this cold water. So it will start to rise up and fill. And what is the time it will be taking for uh, filling the containers? What is the time that is required? We'll derive an expression for that time. Okay, this is a very interesting question, right? Okay, so let us first define our coordinate systems. So let us take this direction as x direction. So x direction. Okay. And we will be having similarly gravity along the bottom direction. Along the x direction only, we can say, let's say we have along this, we have g. Okay. So I'm writing it as a question, but it's just, I'll tell you how to do this. Okay. The length and diameter of the cylindrical container are L and D, that we already know. And the temperature of the wall is maintained at Ts due to this cold water. Okay. So the liquid mass in the container can be expressed as, let's say, let's say if this is the x direction, then we can say that, say for example, up to this length from the top is x. Okay. And therefore, if this is very thin, let's say if these are very thin, very very thin, then we can say that the mass, liquid mass in the container, we can write this as, if from here to here, if this is x, so let me write, if this is the x direction, we can write, let's say from this point to particularly up to this point, let this be x. How do I write it? Oh, just take this as x. So if we subtract it from the total length, so that is L minus x. So we have L minus x. So this is nothing but the length of this particular, from this to this, is nothing but L to x. Okay. And we have, say, some area multiplied with some cross sectional area. So this is the total volume that this liquid is occupying, and the density of the liquid that we have is equal to nothing but the total mass that is accumulated inside the cylindrical container. Right. Now this is mass, and this mass is changing with respect to time that we have taken, that this mass will be changing with respect to time. So we can write the change in mass is nothing but dm by dt. Correct. So if we substitute this back in here, we can write it as this dm by dt as d by dt of rho l ac times of l minus x. Correct. So you see this density of the liquid, area of cross section, these are all constant. Only this x is changing because more and more, as more and more liquid is accumulating, this x will be changing. So this will boil down to, we can write minus times of rho L AC times of dx by dt. Correct. Now where from this mass that is accumulating, from where is it coming? So if you see how much, how do we calculate it here in the previous question? You saw that the heat, when we equate it to this heat, then we see the rate of heat transfer is equal to the energy required for phase change times of the mass flow rate. Correct? Similarly, we can write the same thing here, that Q dot is equal to M dot times of H F G. Okay, and this M dot here, you see these are condensing. Okay, so we have a phase change, and therefore the rate at which it is condensing is nothing but the how what rate this mass is changing at the bottom, because the rate at which it is condensing, it is going down and changing the mass at the bottom. So this is nothing but we can write this H F G that we have, that will be there, and here we have M dot of T, this same M dot. But what about this Q dot? Is nothing but the heat transfer by convection, because you see we have a cold water and the cold water is taking away the heat. So this is by the heat is going out by convection. So we can write it as some heat transfer coefficient. The surface area, here we will write AS, because this was bottom area. This is the curved surface area times of, we have T sat, that is the saturation temperature at which it is condensing, minus Ts, that is this temperature outside. That is this Ts at which it is maintained because of this cold water. Therefore, we can just write m dot of T, nothing but H bar As T sat minus Ts whole divided by HFG. Okay, so this is what we got for m dot. Now, what is this average heat transfer coefficient H bar? So, you know this expression for H bar that we have derived, you have seen in your lectures also. So, this average heat transfer coefficient is equal to how much? We have 0.943 something something, some constant, and then we have this G rho, sorry, this G, we have density of liquid times of rho L minus rho V times the heat transfer coefficient of the liquid side Q HFG, this thing divided by, we have mu times of T sat minus Ts times of X, and then this raised to power of 1 by 4. Right? So you can substitute this, here. So by substituting this here, you will be getting the expression for m dot of t. So let me write. So we have m dot of t. This is equal to how much? Uh, Instead of h, we can write this particular expression. So let me just copy it. And then we will be multiplying it with the curved surface area, that is pi times of d times of x. Okay, because this a is only from region where we don't have the liquid. So here up to which liquid has filled up, here it is still empty. So we can still have convective heat transfer very well because of the film. So we can write this as pi d times of x. So this we have substituted. This, let me do with red. So this we have done. This also we have done, pi dx. And then we have ts minus tsat. This is t sat minus ts. Okay. And this entire thing divided by hfg. So this is nothing but m dot. So you see, this m dot, we need a expression in terms of x. So here we have x, and here we have x. So we'll simplify this m dot to a good form in the form of x. So let me write. So we can write m dot of t is equal to, we can write, let's say 0.943. Then we have pi and d. Let's say pi and d we have. And then we have hfg at the bottom. So we can write that also. hfg. Okay. And then we have the terms in the, all the terms in the bracket. And if you just get this tsat minus ts inside, so it will be to the power of 4. And here we have 1, so it will be cancelled out. Okay. So let me copy this particular expression so it will be easier. Mm, Copy, paste. Okay. The only thing if you do is this will turn out to be cube because this will go in, and this x we will be removing from here. We will be taking that out. Okay. So if we do that, we will be getting, let's say we do it here L, let's say, then we can have L by x cube, sorry, x to the power of minus 3 and to the power of, we will be having 1 by 4. Okay, so now we can substitute the expression for m dot from here. This is nothing but, this implies we can write minus rho L AC times of dx by dt, right? And that is equal to this particular expression. So what we can do, we can take this to that side, okay, and a dt here, and a rho LC we can write it here. So let me write it. So we can write, mm, so here we will be having, this will go out, and here only L will be there. So delete. So we can write L to the power of 1 by 4, and this HFG term will be there, but alongside HFG we have other terms, that is rho L and AC, right? And this will be equal to, and this is, this will be here x to the power minus 3, minus 3 by 4. I think this will be x cube, right? Not minus 3. X cube. Yes. So here it will be x to the power of 3 by 4. X to the power of 3 by 4 times of dx. And this is equal to, and here we will be having, then we have one minus sign as well, and then we can just have one integration, and similarly here also we can have integration, right? And this is from, and here we will be having dt, so 0 to tf, and x is from, we will be having L to 0 because it's in opposite direction. Okay, so if we do that, we will be getting, this will be x to the power of, I think I am doing some mistake, right? This will be minus 3 only. Minus 3. So it will be minus 3. So here it will be x to the power of 1 by 4 divided by 1 by 4. And from L to 0, the minus sign. And this will be equal to this entire term multiplied with TF. Entire term will be there multiplied with, let's say, TF. Right? And if you substitute this, this will be L to the power of 1 by 4. So 4 times of L to the power of, this implies we can write 4 times of L to the power of 1 by 4. And this is equal to this particular or in this entire term. So to find out TF, you can just rearrange it. This implies TF is equal to, you can just rearrange it. So I'm not doing it. I'm just writing the final. Let me see. This is the final answer we are getting. 4.24 times of HFG uh, rho L times of AC. This whole divided by of, we have this whole thing divided by, we have we have G rho L times of rho L minus rho V times of KL cube times of HFG divided by mu times of Tsat minus Ts times of cube times of L. Okay. And here we have pi d and to the power of 1 by 4. So this is the time that we are getting. So this is the time in which it will fill up the cylindrical container. Okay. So that's it for today. So we'll practice more such questions related to next week's course content, and we will meet again next week. Okay, with more questions to practice. Okay. So till then you practice and meet you again next week. Thank you.